We've already talked about gases, and part of the definition of gases is that the particles of gases are so far apart, there's so much empty space between them, that these particles do not interact. And that's part of the definition of a gas. But as we cool that gas down, and we'll get into the energetics of this, but as we decrease the space between these particles, our particles start to interact. And when they start to interact, they change phases. Again, we'll talk about those energetics here in a few minutes. But right now, what I want to talk about is how these particles interact with one another. Now, we're not talking about, say, if I was going to draw this out, this is a Lewis structure. And this Lewis structure, although that's not going to work, this Lewis structure shows the structure of what's called dimethyl ether. So this is a liquid for all intents and purposes. And what we're showing here, these lines are bonds. That's not what we're talking about with intermolecular forces. What we're talking about is the interaction between two different molecules of the same liquid. So how do these molecules interact here? That's what we're going to be talking about. Now, these intermolecular forces are not bonds. That's very important. And we have three primary intermolecular forces that we'll talk about, and I'll give you a little taste of what the others are in case you need that later, but not for my class. So what we have what are called dispersion forces. Now, dispersion forces can be called London dispersion forces or just dispersion forces. It depends on where you're looking this up or what part of the country you're in, which is more accepted, or even which place in chemistry you are. If you're in general chemistry, usually we just call them dispersion forces. But once you get to organic, for some reason, we change it to London dispersion forces. So either way, those are the weakest of our intermolecular forces. Then we have what are called dipole-dipole interactions. And the dipole-dipole interactions, that's our intermediate force. That's our medium range force. Then we have the strongest of the intermolecular forces we're going to look at least in my classes, and that is the hydrogen bonding. Now, it's very important that although it's called bonding, this is not a discrete bond. It is many orders of magnitude weaker than an actual bond. Now, dispersion forces or London dispersion forces, this is going to be with all molecules. All compounds and molecules are going to have dispersion or London dispersion forces. Specifically, we assign the dispersion forces to non-polar molecules. So if you need to go back and review your shapes and dipole moments, this would be a real good time to do that, because we need those non-polar molecules to assign to our dispersion forces category. For our dipole-dipole interactions, those are going to be our polar molecules. Well, that's great, because then we've really taken up just about all of our molecules. They're either going to be polar or non-polar. So what's with hydrogen bonding? Well, hydrogen bonding is a special case dipole-dipole interaction. And that's where you have a hydrogen that is covalently bonded to a nitrogen, oxygen, or fluorine. For example, water undergoes hydrogen bonding. So does ammonia, you see, because there are covalently bonded hydrogens to an NO or F. All of our other polar molecules are going to end up dipole-dipole, and then our nonpolar molecules will have dispersion forces. Now, each molecule that has hydrogen bonding also has dipole-dipole, also has dispersion forces. So usually when we classify these things, we classify them by the strongest intermolecular force that the compound can participate in. Now, the stronger the intermolecular force, the more energy is required to remove one molecule from the other. But really, what are we looking at here? Well, let's look at water. This is water. We know water is a bent molecule. It has these lone pairs of electrons out here. So we have this partial positive, and then we have this partial negative on the molecule. It's a polar molecule. When water is a liquid, it orients so that the partial positive of one molecule is looking at the partial negative of another molecule, because opposites attract. So this business here that I'm dotting, this is the intermolecular force. Now, liquids are pretty cool in the idea that they are not permanently bonded to their nearest neighbors. They slide around. And because they slide around because of these intermolecular forces. And these intermolecular forces will give them a lot of properties. Now we're going to talk liquids specifically in the next video, but I need to set it up with these intermolecular forces here. We can organize a group of molecules by their relative boiling point if we know which intermolecular forces are the strongest forces that they interact with and their molar mass. Because the stronger the intermolecular force, the more energy it takes to remove one molecule from the other. So the more energy it takes to remove one molecule from the other, the higher the boiling point. And that's why molecules with hydrogen bonding classically have higher boiling points than molecules that only participate in dipole-dipole interactions of the same mass. And conversely, or similarly, have a higher boiling point than those that only have dispersion forces. Now, dispersion forces being the weakest of the intermolecular forces, it doesn't take much energy to remove one molecule from the other. And that's why the boiling points are much lower for those that only have dispersion forces. So if we have some group of compounds, just this group of, well, let's put ammonia in there too, this group of compounds, and we need to rank them from lowest to greatest boiling point. The first thing we ought to do is put them in their categories. Which only has dispersion forces, so we need our nonpolar molecules, which are polar that do not participate in hydrogen bonding, and which participate in hydrogen bonding. Well, I used water and ammonia over here for my hydrogen bonding example, so we can just toss those over there immediately. Neon will only have dispersion forces. There's nothing polar about it. It's a nonpolar, it's just an element. It's an atom, so it's nonpolar. Hydrochloric acid, now we do have a hydrogen, but it's not bonded to an N, O, or F. So this only interacts with, or the greatest interaction is a dipole-dipole interaction. Methane. Now methane, remember from our shapes module, that methane arranges with its Lewis structure sort of like this. So it's in a tetrahedral shape. That's both its electronic and its molecular geometry. And all of these dipoles point towards carbon, but because these orbitals are hybridized, they are pointing in equal and opposite directions. So methane is a nonpolar molecule. The strongest intermolecular force it will have is a dispersion force. Similarly, carbon tetrabromide, also with the same geometry, will only have dispersion forces. Now, this molecule here, it's tempting to call that a linear molecule, but it's not. Remember that oxygen has these two lone pairs, and its electronic geometry is tetrahedral, even when the molecular geometry is bent. So that makes this a polar molecule, and that's going to go right here. So now that we've organized them by intermolecular force, strongest intermolecular force, now we need to analyze them for their mass, their molar mass. And we do that because the larger the mass, the more interaction there will be. Kind of like the larger the planet, the more gravitational field it has. So we look at these by mass. Now neon has a mass of about 20, and I'm just going to round here. Methane, we got 12 plus 4 is 16. Then we have carbon tetrabromide. So bromine's actually very heavy. Bromine is about 80, and we have 4 of those. So we're looking at greater than 340. That's really what it comes down to. We would be more precise if we were close in any way, and we are not. So with the dipole-dipoles, we have hydrochloric acid with about 36. Our dimethyl ether here is about 46. Water has a mass of about 18, and ammonia has a mass of about 17. So now we can put these in order. Now, purely based on the intermolecular forces and the masses that are provided, the lowest boiling point, given this general rule of thumb, would be methane, followed by neon, and then carbon tetrabromide. Then we would move to the dipole-dipole interactions. And then we would have hydrochloric acid and dimethyl ether, so CH3OCH3. Then we would move to the hydrogen bonding. We have our ammonia and then water. Now, even though ammonia and water have much smaller masses, they are expected to have much higher boiling points. Again, these are not absolutes. This is just a general trend to give you an idea of what kind of interactions we're dealing with and the energy that may be involved in order to break apart these interactions. The reality is, carbon tetrabromide has a much higher boiling point than even water. So, if asked to rank a group of compounds based on the intermolecular forces rule of thumb or general trend, you would be expected to rank it in this order. So those that only have dispersion forces should be ranked lower than dipole-dipole interactions, which should be ranked lower than hydrogen bonding. Again, it's just a place to start as we start talking about the properties of liquids and solids.